because so you need a value here, so you need a receive before this, right? You need to receive x here before you can actually use it, and you cannot send x before this because it is modifying x, right? I hope everybody is okay with that. So those things will come into consideration later. So some of the terminology from the SPIMD word. There's something called owner computes rule. So now you have like many processors. Okay, this is a SPIMD setting, single program multiple data. You have many processors executing the same program in MPI style, and you don't know, like, given a certain computation, who executes this computation? There are many processors. I mean, where does this get executed? So what you assume is the guy who owns X here will do the computation, and these values which are being referenced, those will come from other processors. Okay, so that is the owner compute rules. The guy who owns this will actually do the computation. Okay. Then there are things like communicator descriptor, where all the non-local references, by non-local references I mean the RHS references which are being communicated to this particular processor, those are modeled as descriptors in the data flow analysis. We'll see what that means. Then, as I said, there are header and last nodes. And there are these particular edges. So this is the entry edge from the header to a node in the loop, and this is the backward edge. And all other edges, all other edges, those are forward edges. That is some terminology, I think, but it's finally we have just two elements in the lattice, top and down, to start with, because we just like for send placement, we just need to know whether placing a send at a node is safe or not. So that is the binary decision there. But after that, yeah.
So when you said communication descriptor, like you said that's a reference to data on a remote processor. So is this like a partition global address space, or is that like somehow correspond to the sends and receives, or something else?
Well, it just corresponds to the receives.
Okay.
Because you are receiving this, I mean, so this is like what, x 1000, right? 1 to 900.
Okay.
So that is modeled as one communication descriptor in the data flow analysis. So these are just non-local references, and we denote them by a communicator descriptor.
Okay.
Nothing else. So you can see that x is going from 1 to 900 here. That is the same as xi here. Loop bounds are the same. So basically it's the same array.
Okay.
But we model them as distinct communicator descriptors. So we are basically saying that this is a distinct LHS reference, RHS reference. Yeah, so we add this unbalanced element afterwards when we want to place a balancing receive for the sends that we have placed. Okay. So what does it mean for a node to be safe? Can you see that?
Not very well.
Can we?
Okay, I'll just explain that.
Well,
Might help to try.
yeah, dimming the lights might help.
Lights?
Yeah,
It's already on.
Behind you.
just the front one's a little bright.
Okay.
I can live it.
Okay, I'll just explain that. Sorry. So what does it mean for a node to be safe? So as I said, if the data is being used at a node, then you have to place a send there, right? Because you have to send that data before somebody is using that data. Okay? So this is a use of xk, and this is being used by some processor that is doing this computation. So you have to send xk before it is being used. Send xk to the processor that will do the computation. Okay. So this is like a distributed memory stuff now. I mean, you have multiple processors, and xk is actually distributed. Yeah.
So just based on this graph, how do we know what processor X is on or what processor W is on, or like how do we know where these variables are?
Well, that is, we're not modeling that right now. We're just assuming that it's a block distribution for all the processors, and we just know that xk has to be communicated.
Okay.
I mean, it can be any processor, but just xk has to be communicated. After we have placed the send and receive calls, then there is a later phase where this will be translated to MPI.
Okay.
But we know that this is a block.
So we're basically assuming anytime you refer to a variable, you have to either send or receive, and then maybe later we have a pass where we say, oh, I'm sending and receiving, or I'm sending to myself, so I might as well just not do anything. Is that the idea?
Okay, so it's a block distribution, right? I mean, so xk here has to be sent, because this computation will happen on every processor.
Okay.
And xk is distributed. Some part of xk is distributed across all the processors. So you have to send that here.
Well, except for the block that's on your own processor.
Yeah, that's true. Okay. So yeah, as I said, like the MPI sends and receive, those will be placed in a later pass. So as I said, you have to have a used at the node n for there to be a placement of send, right? You have to place a send if there is use at node n. So that is this condition, used ND. We're saying that the descriptor or the data referenced by descriptor D is being used at node n. So it's a safe place of send. Or so trans ND means that D is not being modified at n. That is this predicate. And this says that for every successor of this node, you can place a send for D there. So, yeah, sure. So you have a node here, and you have multiple successors. Now you know that it is safe to place a send for D on all these nodes. So you can take that send here as well, right? And place the send here for D. So that is what the intersection means. And the trans just means that it is not being modified. Okay. Now the header nodes have to be a little. We have to be a little tricky about header nodes, because so you can see that you have this loop over here and this forward branch over there. So if I wanted, so xi needs to be sent. Now I can take this back here, but I can take this back, the xi sent back across this branch, right? But because xi is being modified in this, you cannot place the send somewhere like in this node, right? Because that is a modification. So we have to be careful about loops a little bit. So what you do is, when can we take the send and pass this header node? So when all the forward edge successors are safe, and when we can place the send inside the interval, right? Then we can take that send and bypass the header node. Okay. So that is what is being said in this particular data flow equation. So H is the header node, M is the immediate successor of H in the interval. So if you prove that it is safe to place send for data D in the immediate successor, and for all the successors of H, forward edge successors, these are not in the interval, it is safe to place send, then you can hoist the send across the header node. Hope that was clear. Another thing that you can do is, now you want to move the sends as far back as possible to the start node, right? So the sends have to be moved in this direction as far back as possible, and the receives have to be moved in this direction as far as possible. So that now the send starts, it's going on somewhere, and you can do the computation. So that is what is meant by communication-communication overlap in this case. Okay. Now, as I said, it might not be safe to hoist send to somewhere like here, because the data is being modified in this loop. Similarly, receive. If the receive data is needed in particular node, you cannot place the receive after. So these flow equations will tell you what is the earliest place that you can, what is the earliest node that you can place the send at. It's more or less the same. So this is a not safe. Okay. So it is just saying that for any of my predecessors, placing a send at that predecessor for data D is not safe, right? So that is the earliest send. And this is again the loop condition. It is just saying that the forward edge successor in the interval of the header is a safe place to put the send. So this is the example I was talking about. Now